Hello, folks who have joined. We're just waiting a couple more minutes before we'll start the webinar. Thank you for your patience. Okay, well, folks, it's top of the hour, so I'll go ahead and start to share my slides. Okay, hopefully everybody can see this acceptably. Good morning, good afternoon. My name is Brad Suessmith, and I'm a Robotics Sales Manager at Orbbec. I'm based in Austin, Texas, although you can probably tell from my background, I'm actually in a hotel room in Chicago at the moment at attending the FabTech conference up here. And I've provided my contact information in the title slide here. Feel free to reach out to me after the call, after the webinar, either by email or by phone. And today's topic is Orbbec's brand new 3D LiDAR. We believe it's the world's first multi-pattern LiDAR in the industry. And our tagline for this product is one sensor, many possibilities. So here's the outline of my presentation today. I'm going to start off by giving an overview of Orbbec, the company, for those of you who are not familiar with Orbbec. And then I'll talk about some of the development goals of the sensor, some technical highlights of the sensor design, and then some of the use cases that it could be deployed into. And then we'll wrap it up with a conclusion and then move to Q&A. I did a timed run of this presentation just a few minutes ago, and I think we'll have plenty of time for questions. So feel free to add your questions into the chat at any time during the webinar, and we'll address those at the end. And if there's any questions that I'm not able to answer, we'll follow up after the webinar with detailed responses with the help of our product management and engineering teams. Okay. So first off, an overview of Orbbec. Orbbec is a mature company that's been around since 2013. So we're a 12-year-old enterprise. Our global headquarters are in Shenzhen, China. And we're a publicly traded company on the Shanghai Stock Exchange. Back in May, our market capitalization was just over $3 billion. I checked yesterday, and the China stock market's been going up quite a bit recently, so we're now at about $4.25 billion valuation. Last year, we did about $80 million in revenue, and we've been growing very quickly and strongly. So this year, we expect to be far above that. And our primary market is robotics, and we have about 70% market share in the depth camera industry for service robots, which would include robots that do food delivery in restaurants, perhaps, or hospitality robots that deliver mail and small packages in hotels and in hospitals and environments like that. We've listed some of our key ecosystem partners and customers at the bottom here. Obviously, in the robotics space, which is my focus, NVIDIA is a key CPU and platform partner. But we also have partnerships with Microsoft, which I'll talk about in the next slide, AMD, Hitachi, Jabil. Universal Robots is one of our lighthouse customers in the robotics space. And then our cameras actually get used quite often in face authentication applications as well. And in that place, Alipay through Alibaba and Oppo are also key customers. And I didn't really mention our primary product line is depth cameras and LiDAR sensors. We also provide ODM and OEM design services and manufacturing services. And we just opened a new factory in Foshan, China, which is about an hour and a half northwest of Shenzhen. There's a small picture of it on the right side of the screen there. We opened that in October of last year. It's a huge facility with a lot of space. And this is where we currently build all of our sensors and robots that we build for our clients. And then our headquarters building is also quite new. It's probably about a year and a half old. And that's actually located in downtown Shenzhen. You can see a small thumbnail image of that there on the left. But we also have offices around the world. Our North American headquarters are in Troy, Michigan, just 30 minutes north of Detroit. And then in Europe, our headquarters are in Munich. And due to our manufacturing capabilities and our vertical integration, we have quite a few employees. We're currently at about 800 employees and growing quickly. So this is a snapshot of our current sensor portfolio. We're a little of a bit of a unique company in the depth camera space because we're the only one that I'm aware of that offers cameras utilizing all three of the major technologies. So we have a wide variety of stereo vision cameras. We offer structured light cameras and time-of-flight cameras. And the reason why this is important is because depending upon the lighting conditions of the scene, the speed and range of objects in the scene, cost considerations, power considerations, physical size constraints, different technologies work better than others. There's no such thing as a universal technology that works best in all applications. And the really neat thing about Orbbec is that we offer a unified SDK that supports all of these different types of technology-based sensors. So you don't have to rewrite your code if you switch from a stereo camera to a time-of-flight camera, or when you intermingle different types of products in a single design. So starting off at the top, the stereo vision cameras, we offer a variety of baselines for different operating ranges. We also offer a variety of models with and without NIR filters to reduce reflections in scenes. And then we offer a variety of interfaces ranging from USB to GMSL FACRA to Ethernet and power over Ethernet interfaces. And all these cameras include a variety of intrusion protection ratings varying from IP5X to IP67 ratings, depending upon the model. And stereo cameras tend to be very popular in mobile robots for obstacle detection and collision avoidance use cases. And then the structured light family, we have two products, kind of an entry-level product and a higher-end product. These tend not to be used as frequently in robotics applications. They're more useful in high accuracy applications such as 3D scanning, where you want to create a 3D model of an object or a human body. The time-of-flight family is derived from the Microsoft Azure Connect technology. When Microsoft exited the depth camera business about 2 years ago, they transferred the IP and supply chain over to us. So we have a direct replacement for the Microsoft Azure Connect DK camera. That's an entry-level USB product called FemtoBolt. And then we have a couple of versions where we've integrated a Jetson Nano into the design as well. Those are FemtoMega and FemtoMega I. And these have the added benefit of a PoE interface on the back of the camera. And then in the LiDAR portfolio, the existing LiDAR portfolio is based around two products. We have an entry-level product called MS200K, which is more of a consumer-oriented LiDAR. You could view this as being something that you would find in like a Roomba-type vacuum cleaner design. And then we have an industrial-grade planar LiDAR device called SL450. It's a 270-degree planar LiDAR. And I'll be referencing that throughout this presentation as well, because some of the characteristics that we incorporated into that design have carried over into the new design. And then for retail store applications and healthcare applications, there's a lot of customers in that space that desire to have an integration of the depth camera with a computer. And so we've got 3 products in that space that combine those 2 functions together. So that's kind of a quick overview of our existing portfolio of sensors. So now I'll move on to the development goals for the new sensor, which is what I'll be covering in the rest of the presentation. So with current LiDAR sensors, one of the challenges is that they often lack flexibility. Typically, they'll offer a single scanning mode, which means that you may have to use multiple sensors in a single design, or you may need to sacrifice performance because you can't really change the way it operates. Usually you can change the rotation speed of the sensor, but that's about it. Another challenge is that in complex reflectivity environments, such as this scene here, street scene, where you've got varying degrees of reflectivity from black, low reflective objects to bright white and yellow reflective objects. Current sensors often produce inaccurate or distorted data around those features. They can't distinguish well between the different reflectivity levels in a single scene. So that can cause errors in your data stream. And then they often also suffer shortened range in bright, sunny conditions, and either shortened range or they generate noisy point clouds due to the interference from the sun. Since most LiDARs operate with a near-infrared laser at a wavelength that the sun emits a lot of energy as well, that tends to be a significant problem outdoors. And then another issue, typically more indoors, is multiple LiDARs operating in a shared environment will often interfere with each other and generate crosstalk noise, which again produces errors in the output of the sensors, making them less reliable. And then finally, another big challenge in the LiDAR industry is traditionally they've been very expensive sensors. The costs have come down in the last 5 years or so, but in general, LiDARs are significantly more expensive than a stereo depth camera or structured light depth camera or time of flight camera even. And so this causes people to be very picky and choosy about where they deploy LiDARs and how many they deploy. And often they will combine LiDARs with lower cost depth cameras to try to reduce the cost of the system and still maintain the functionality that they need in the design. So our solution to this is called the Pulsar ME450. We announced this product at the World Robot Conference in Shanghai about 2 weeks ago. And we believe it's a high performance, cost effective, multi-pattern, direct time of flight 3D LiDAR that will revolutionize the LiDAR industry. So some of the development goals for this product were to create a new scanning architecture, which solves the flexibility problem. We wanted to maintain the excellent performance in terms of range and noise characteristics and accuracy characteristics of the existing SL450 Pulsar LiDAR. And we also wanted to maintain the stability and reliability and industrial grade ruggedness of the SL450 product. And then finally, we wanted to make it more developer friendly. Previously, we had one tool chain for our LiDAR family and a separate tool chain for our depth camera family. And that often caused increased development effort and potentially delays in people's development. So we wanted to help ease that friction. So here's some highlights of the new sensor. It incorporates a very innovative scanning architecture, which we think is very unique and hasn't been deployed before. And we've heavily patented this design, and you can see an animated GIF in the main body of the slide here. Essentially, it's composed of two primary moving items. There's the traditional rotational motor that rotates the sensor around in a 360-degree pattern. But then the really innovative part is we utilize a MEMS mirror, which moves in a vertical motion in a range of 15 to 30 degrees, which provides a varying vertical field of view at the same time as it's rotating horizontally. And we can couple and decouple these two motions together to come up with different scanning modes, which I'll talk about in the following slides. So they're at a high level, there's two essential or two basic modes. There's repetitive modes where the MEMS mirror and the rotor or motor rotating the rotor are coupled together and synchronized. And then there's a non-repetitive mode where the two are totally decoupled. So in the repetitive mode side, which is illustrated by the GIF on the left, we have multiple density modes as well, or sub-modes you could view them as. So in the basic non-dense mode, you'll see this illustrated here where you have a sinusoidal type of scan pattern across the scene. So you're getting a lot of pixels repeated in the point cloud over and over and over. So it quickly generates those data points, and they're quickly updated and repeated. What's not shown here is that we can also have this and divide by 4 as well. So you can get overlapping sinusoidal patterns that are 2 times as dense as what you're seeing here. And then also another mode where it's 4 times as dense. And again, that's because the mirror and the motor are still coupled together and synchronized. And I'll get into the use cases for this in a bit. In the non-repetitive mode, the MEMS mirror and the motor are totally decoupled and more or less move randomly in relation to one another. And that's very useful because it can then create a complete point cloud image of the entire scene. You'll get pixels or voxels for every point in the scene, essentially recreating the field of view and data that you would see from a depth camera. So very dense, very rich information. However, it takes a while to accumulate all that data. So it's not useful in all use cases, but can be combined with the repetitive modes to add that flexibility that I talked about at the beginning. So here's some static images which illustrate these varying degrees of density using this scene here at the top, where you have some panels with varying reflectivity from highly reflective white surfaces to lower reflectivity gray and black surfaces. So starting from the left, you'll see this repetitive scanning mode. Again, this is the non-dense mode, so it's essentially the 1x mode. You can see the sinusoidal pattern and the varying colors representing the different distances to the targets in the scene. And then in the repetitive scanning mode, you'll see that the same sinusoidal pattern, but much denser. This is probably the 4x mode. And then you can see additional detail here for like this white target here and the red. And then in the non-repetitive scanning mode, it's virtually there's no blank space in the scene wherever there's a reflection from a target. It's very dense, almost like what you would see from a traditional stereo depth camera. And again, very good definition of the white objects versus the black and gray are clearly highlighted. So some of the use cases for these different patterns and modes. So if you're building a robot that's and the function of the LiDAR is to do SLAM mapping and navigation, you may want to start out with the non-repetitive scanning mode when the robot's stationary to build up the complete map of the environment that it's operating in. And that's signified by the 1 and this little star here. And then once the robot starts moving, you may want to switch to a non-dense scanning mode, the repetitive scanning non-dense mode, to quickly update the robot's location within that dense map as it's moving around. For obstacle detection, you kind of want something in the middle because you don't want the robot's moving, so you can't wait for the repetitive scanning to build up the full scene. At the same time, you don't want it to be a low density point cloud because then you may miss a relatively small object or narrow object like a small pole in the field of view. You might miss it. So you probably want to choose one of the repetitive scanning but denser modes like the 2x mode or the 4x mode in that case. And then if you're using the sensor for surveying a scene or scanning an object to create, again, a 3D model of an object, then you probably want that non-repetitive scanning mode as well, because that will give you the highest number of data points to give you the most complete point cloud of the scene or the object that you're scanning. So as I mentioned earlier, it was important for us to maintain the accuracy and precision levels of the SL450 LiDAR in this new design, while adding the new multiple flexible scanning modes as well. And you can see from this lab testing that we did that with the maximum sampling rate of the LiDAR being 200 kilosamples per second, its accuracy level is within 30 millimeters across a wide variety of reflectivity levels, as low as 10% to 90%, which are the two standard ratings that we use for the industry uses for range, and then for reflective signs that are designed specifically to focus light back to the sender at like a 300% level. It still performs very well, very high accurately in that wide range of reflectivity environments. And then likewise with precision, which is the repeatability of the data that the camera or the sensor is generating, it's within 20 millimeters at that same sampling rate across a wide variety of reflectivity levels. And that's important for ensuring repeatability and robustness of the design. And these charts kind of illustrate this visually. So we have this target scene here with some street signs, speed signs, warning signs, directional signs, and then some blank panels of varying colors. And you'll see that in a traditional mainstream multiplanar 3D LiDAR, you're getting data, but it's not very well defined, and you're not able to see the details of the changes in reflectivity from, in this case, in this sign here, yellow to black, or from, white to red to black. It all looks somewhat uniform to some degree. Whereas with the Pulsar ME450, you're clearly seeing the different reflectivity levels of the different items in the scene. So in fact, the black arrows on this yellow sign are pretty clearly defined in the point cloud, and even the digits on the speed limit sign here are clearly visible. So it's definitely a much richer data set, and provides much more useful reflectivity level information compared to traditional LiDAR sensors. So yeah, another design goal again was to maintain that industrial grade reliability. So the MEMS mirror architecture that we use, the components in that system are automotive grade components. So they're designed to withstand, the shock and vibration of a mobile robot traversing a concrete floor in a warehouse with, cracks in the concrete, and going over rumble strips or cords or whatever it happens to run over on the floor. Likewise, the sensor is IP67 rated, so it's dust proof and water resistant, and in fact, it can be submerged for 30 minutes in a meter of water with that rating. So it makes it suitable for outdoor robots that have to operate in all kinds of weather conditions. And then we've implemented a multi-echo interference mechanism or reduction mechanism that looks at the levels of return from the laser and can clearly distinguish between dust or fog or any kind of particles in the air, rain, and distinguish that between solid objects that you're trying to image. And that's a pretty unique feature, something that we've enhanced over the algorithm in the SL450. And then we've also implemented some unique coding technologies that enable the LiDAR to reject interference from the sun, and also interference from other LiDARs to eliminate that crosstalk problem that I mentioned earlier. So as I talked about earlier, that our SDK for our LiDAR family traditionally was a separate product. We've now merged that into our Orbbec SDK suite. So developers can leverage the same Orbbec viewer that they're used to working with our depth cameras. It's an open source SDK available on GitHub, free of charge. It's cross-platform. It works on, Linux, Windows, Android, Mac OS. And we also include ROS and ROS2 wrappers for customers who need it. And this really, we believe, lowers the barrier to do camera and LiDAR integration. A lot of times, particularly for mapping, you need to fuse data together between the depth cameras and the LiDARs. And by having a single SDK, that makes that process much easier. And, once customers get their hands on the camera or the sensor and start developing with it, if they discover features or functionality that needs to be improved or added, we're very open to requests for adding those features. This is a new development for us, so we're looking for input from customers like yourselves as to how to improve the SDK to make it as easy as possible to use and as powerful as possible. And we are sampling the sensor today, and we have a full data sheet available. And I believe Miles is going to be sending this out to everybody who registered for this webinar. And we have a CAD model as well available. So feel free to contact your Orbbec salesperson to obtain that information. So here's the key specifications for the product. You'll find more detail in the data sheet, but I wanted to highlight some of the things in green here that I didn't discuss earlier. So again, the range of the sensor is up to 45 meters, assuming a 90% reflective target. At a 10% reflectivity level, it's 15 meters. And in both cases, it can operate down to 10 centimeters. The vertical field of view is selectable. I alluded to this earlier, but the default is 60 degrees, but you can also decrease it to 45 degrees or 30 degrees to improve the vertical resolution of the sensor. The horizontal rotation frequency can also be adjusted anywhere between 10 hertz, 15 hertz, or 20 hertz. And the interface to the sensor is a 100 megabit Ethernet connection. It connects through an 8-pin M12 connector on the back of the sensor, and the cable is actually a separate cable, so you can detach it and attach it to the sensor. It's not integrated, so you don't have to worry about the cable wearing out or breaking over time. And the sensor does support precision time protocol and GPS and PPS I/O, so you can synchronize it with the GPS receiver if you've got an outdoor robot and with other PTP capable sensors. It can operate in up to 80K lux of light levels. Again, that goes back to the sunlight discussion I talked about on the previous slide. That's pretty impressive levels, and that is an improvement over our SL450, which was rated to 60K lux. And it still employs a class 1 eye-safe laser, so there's no problems with children or pets or anybody staring at the sensor close up. It won't harm your vision over time. It's a very safe product. And it has a very wide operating temperature, so -20°C up to 55°C, so it can operate in all those outdoor conditions that we talked about earlier. Okay, now I'm going to move on to some of the use cases for the sensor. So again, because I'm robotics focused, I like to talk about warehouse robots. 2 examples here, like autonomous forklifts or pallet or box mover type skateboard robots. These are kind of the two of the most popular type of form factors in warehouses. And we're showing a animated GIF here of a mobile robot moving through our warehouse in Foshan and building up the point cloud and map of the environment. And as you can tell, it's a very rich map showing fine levels of detail throughout the facility. So again, this is a perfect example of the mapping capability that the sensor enables for your robot design. Just let this play a little longer, so you can see individual boxes and pallets up on the shelves. It's pretty impressive. And then for outdoor robots, likewise, we're showing here a autonomous lawnmower operating in a field in Shenzhen, building up a map of the trees and the landscape that it has to navigate around and maintain its proper positioning and location within. And because of the tall vertical field of view of the sensor, it could also be used for obstacle detection at the same time that it's being used for the mapping function. So if an animal runs in front of it or encounters a ball or some toy or some other kind of object in the scene, it can use that the sensor's detailed information to navigate around the object. And then likewise, these same features and capabilities of being able to operate in bright sunny conditions are also applicable to autonomous delivery vehicles that you might find delivering parcels or food deliveries in dense cities. And then lastly, again, surveying and scanning, where you want to, perhaps survey a construction site. You need to build a detailed digital twin of your environment to make sure that everything gets placed properly in the first time around, and not having to do rework of the construction afterwards. And also for scanning, again, objects and bodies, and creating detailed 3D models of an item. Um, this sensor is very well suited for that, given its high density, non-repetitive scanning mode, and its tall vertical field of view that gives you that continuous stream of pixels in the vertical dimension. So now I'll wrap it up with a conclusion. So again, the Pulsar ME450 is what we believe is the industry's first multi-pattern, high-performance 3D LiDAR sensor. It offers configurable, repetitive and non-repetitive scanning modes, and high accuracy and precision, and the enhanced anti-interference I talked about in multi-LiDAR and sunlit environments and dusty and foggy environments. And one of the most important things that I didn't mention earlier is the price. Due to Orbbec's in-house manufacturing capabilities and our economies of scale through building the depth cameras and robots and other products that we build, we're able to keep the costs at a very competitive level. So this product's going to retail for $549 US, and that's for quantity of one. It'll naturally decline in price with high volume applications. And we believe this is a very competitive price point. In fact, I think it's lower cost than most of the planar LiDARs in the market today with this level of performance, let alone 3D LiDARs, which tend to be very, very expensive sensors in the thousands of dollars. So this is a pretty exciting development in the industry, and I think it's going to revolutionize a lot of robot designs going forward. We've provided a QR code here you can scan to learn more. That'll take you to the product page, which is listed here as a URL. And again, if you want to get a sample of the sensor, you can submit a form on our website and request it. If you have an Orbbec account manager assigned to you, you can reach out to them and request a sample as well. And of course, any additional information they'll be happy to provide. So with that, we'll move on to the Q&A. And I'll have to exit full screen here mode and take a look at the questions. Maybe I'll stop sharing. Okay. I'm not seeing any questions in the chat window. If you have questions, please enter them into the chat. I realize, unfortunately, this YouTube Studio format doesn't allow for verbal interaction, but if you can please enter your questions in chat, I'll do my best to answer them. So I'm IMing with one of my coworkers. I guess there was a question. How long? Okay, Dan Clemmer asked, how long does it take to accumulate the point cloud in non-synchronized mode? I've actually demonstrated this sensor at a trade show last week, and it only took a few seconds to accumulate, a pretty dense scene. So I'd say less than 5 seconds gives you a pretty dense environment. Obviously, it depends on what level of density you're looking for. The longer you can wait, the the denser and denser it gets. But I'd say after about 5 seconds, it was pretty dense for the human eye to see. At least it didn't seem to improve much over that. But it's something you might want to test in your environment and situation and see how long you need to wait. Thank you for the question. It's a good question. Any others? Mao, were there any other questions? Okay, I'm seeing a lot of thank yous from the WDL team. I appreciate that. WDL is one of our distributors. No other questions, huh? Wow, I can't believe I did that good job of explaining it. But well, if you come up with a question afterwards, feel free to reach out again to my email address. I'll put that in the chat window again, just so everybody has it. And yeah, we appreciate your time and interest in the sensor, and we look forward to talking to you soon. Thank you and have a great day. Bye-bye. Oh, one more thing. This video is recorded and it will be made available on our website, and Mal will be sending out links to the recording, as well as a copy of the slides will be made available to everybody who registered. So if you had a colleague that missed it, you can forward the information to them and they can watch it at their leisure. Thank you again. Have a great day. Bye-bye.